Welcome everybody. My name is Guillermo Pérez. I'm a member of Frank's group and have worked on the many aspects of the software that we are teaching today of PyEMMA. Before I move on, I'd really like to get a sense of who I'm talking to. So who here is just a plain undergrad student? Raise your hands, please. No undergrads? Who here is a PhD student? And the rest are postdocs, I assume? Or? Sorry, masters. Okay, so who here is a master's student? Okay, so physicists, chemists, mathematicians, okay, clever people? No. Okay, so I'm going to be working with another molecule. You work with dialanine, but I'm going to be working with BPTI, which is bovine pancreatic trypsin inhibitor, which is one of the first molecules for which there were very, very long, millisecond long simulations carried out in the form of one very long trajectory in one of these supercomputers that Frank was speaking about today in the morning. So we're going to be dealing with just one trajectory. It's just very long. And we're also kind of doing it with a different set of data. So also to give you the impression that the procedures are always the same. You know, featureize a trajectory, cluster it, or do some dimensionality reduction technique, and then try to get an MSM out of it. And the type of plots that you're going to be looking at are going to be looking similar, regardless if the molecule is dialanine peptide or this BPTI, which I just found out that it's actually also a commercial drug. We didn't know this, so there you go. So we start, as usual, importing PyEMMA to the latest version and loading the notebook with the needed modules for plotting and doing linear algebra, plus some extra functions that you also have to find in your notebooks for plotting and averaging. And we start by loading the topology files into memory, and create a featureizer. In this case, I have chosen to featureize on the set of Cartesian coordinates. It's just C alphas that we're dealing with, so I don't have to specify anything else. So if I parse the top file to the coordinate featureizer method, and I just say add all, I'll be adding, as the description says, all Cartesian coordinates. We have two questions. Please feel free to interrupt me at any time or raise your hand. I'll go to you in a minute.
Are we supposed to download this and follow?
No, you're not supposed to do anything. This is a demonstration. Was that your question as well?
Yeah.
No, this is not a hands-on session. This is a brains-on session. So you look here, and if you find something fishy, you raise your hand, and you ask me, and I'll try to relate to what was explained in the morning session. So far, so good. Am I right? Okay, great. So this is the length of our trajectory. So it's 20,000 frames. It's strided down because the original trajectory is about 10 million frames long. But if I had really loaded that trajectory into memory and started working here today, we couldn't do it live. And 174. Could anybody just out of this number tell me where the number 174 comes from? The physicists among you? So 174 is the number of input.
Because there is like 58.
Exactly. 174 divided 3, because I have x, y, z, gives me the number of atoms. Yeah, there's 56 atoms. I hope. And we do TICA. TICA, as you have heard this morning, hopefully is a dimensionality reduction technique that takes into account kinetic information, and it's optimally suited to build MSMs out of. So we just do it with this method of PyEMMA. The only parameters that we are actually giving is the lag time, which is a parameter of the method specifying at what delay the time-lagged covariance matrices between the input features, those Cartesian coordinates, are computed. Okay? And because I specify, you see my pointer here, right? When I move, because I specify that these are the dimensions that I want, it's going to have two dimensions as it does. So it runs very fast because the trajectory is short, and there we go. One trajectory with 20,000 frames and 2 columns. Now these 2 columns are the ticks, the time-independent components, which when I plot them, they look like this. Actually, because this was inherited from some other notebook, this is 50 nanoseconds. Yes, we're good. So, question. Sorry?
Have we now reduced the dimensions to 2?
Yeah.
Okay.
Yeah, this is this number here. The variable y, this one here, has 2 dimensions. And they are these time traces. So, can anybody tell me, perhaps somebody that has a bit more of experience with tick, what these 2 things are? That's a very vague question. Let's start by saying, what is the relationship between these 2 ticks? What does it mean that the first one is the first one and the second one is the second one?
They explain the maximum correlation in that order. So the first one explains maximum amount of time-independent correlation in the system that we are using.
Yes. Yes, but it doesn't really help me, I think, explain. So, anybody knows PCA here? Raise your hand. Okay, so what does the first coordinate of PCA encode for?
Largest variance.
Largest variance, and the second is the second largest variance, and so forth. Okay, so ticks are, as Ryan said before, there's also a parameter according to which these ticks have been ranked, and that parameter is the amount of kinetic variance, which, because of the way in which the ticks are defined, we're just going to say it's slowness. So these 2 coordinates are ordered by the slowness. Now, slowness here is somewhat a fishy concept, because it doesn't mean slowness in the fact that it's like very slowly evolving. It's slowness in the meaning of rare. It takes very long until you see a transition between the tick 1 having a value around 0 to the tick 1 having a value around 5. Whatever that means, just by looking at this plot, you should say, man, it takes almost 80% of the trajectory of the thing not doing nothing until something happens, okay? Now this something is quick, it goes and goes back, right? And this transition takes just like a couple of frames. So the degree of slowness here, it just means the time scale of the process. If I were to compute the autocorrelation function of this time trace, then it would have a very high time constant, which is what Ryan said at the beginning. And now, obviously, the second one, whatever is happening in the second coordinate, it's happening more often, right? I don't have to wait much to see. And if I were to compute the autocorrelation function, which is, I'm hoping something that helps you put this into perspective, this autocorrelation function would have a faster time constant. And I know that there's a question there. Let me just move on, because these are the expressions of the eigenvalues, which would be equivalent to the variance when we're talking about PCA, expressed as timescales. So these are the exponent of the autocorrelation function if I were to fit it to an exponential function. Okay, so this is like 700 frames for the first one. You see they are all in descending order, because this means that the first tick is slower than the second and the third and the fourth and whatever. Okay, so if you do a tick computation and you check the eigenvalues and they are not sorted by decreasing order, something went horribly wrong. Okay? We did something horribly wrong because we should be the ones writing the code so that it doesn't come out this way. Components don't come out sorted when you diagonalize a matrix. They just come out as eigenpairs. We sort them later. I saw our question?
So the whole, if you go back up to this graph, every single point is from one to another is 50 nanoseconds? Or is the whole thing 50 nanoseconds?
It's every single point is 50 nanoseconds, but even that might be wrong, because I'm just thinking, if the data wasn't strided, this should be like a million nanoseconds. So whatever it is divided by the time step should come out of something like 1. So just ignore this. This is just because it's for a trajectory that was strided with a different TT.
Yeah.
Yeah, just a moment. Even if we, the much clearer unit for our purposes is this, okay? So this is a much more correct unit. This is frames. Whatever the frames are saved in, these are the time units that are internally consistent. So you can put this time unit behind these time scales. These numbers represent frames. These are 712 frames as a time scale for the first tip. 400 something frames. And now if you want to scale that back to physical units, then you go back to your original trajectory and you look at what you squared it with. Martin?
The computation of the time scales, like this lag divided by log of the eigenvalues, I think you can directly compute this out of Tika. Like Tika times.
Tika now does have it?
Yeah, I think so. You've edited it all. Come with this.
Did I write that? Oh yeah. Yeah, there you go. So you don't even need to do this expression to go from the eigenvalues to the lag times. You can use that method now in TIC. Yeah, Martin, you know what happens? This notebook is lastly edited with version 1.2.2. It's like, it's from there up above. So that gives you, an impression. Okay, so we have ticks, we have the timescales, and now we're just gonna histogram those data. I'm hoping everybody's clear to what a histogram is. I'm just gonna put the labels here. Okay, ticks don't have units, and this is the free energy surface. I am hoping that in your minds you're not having much of difficulty connecting this time-dependent trajectory with this free energy where time has been integrated out. Okay, so this is just like the marginal distribution of these two time traces. I told you before, the first tick spends most of its time around the value of 0, doing nothing, then it will jump shortly to a value around 5, and then it will go back. And this is why when I look at the free energy surface, I see that there's much more density around these values here, whereas here there's very little density, right? So the system is mostly here, changing between these two wells, and then it will go here and explore back. Now, because at the center of the Markov state model there's a transition matrix which has been derived from a count matrix, I need to discretize my data. I need to label parts of space with indices, 0 to whatever, the number of clusters, so that I can effectively set up a count matrix. It's the count matrix that Frank showed you today in the morning next to this 4-well potential, right? That had like 4 blobs in the diagonal. That's the count matrix. That's what I will end up doing after I have discretized. So in order to discretize, I just give the y variable, okay, this matrix of 20,000 frames times 2 columns to the method, cluster k means, and there you go. These are the cluster centers. Because this is a k-means clustering algorithm, more cluster centers have been placed where more data exists. That is a feature of the clustering algorithm. And from this moment on, my trajectory is just a series of indices telling me where in space my system, my molecular system is. The nice thing about these indices is that I can use them to construct a matrix of how many times did I visit state 67 before visiting 26 and so forth. Okay, so this is pure publicity now, but we have in the group another piece of software that helps visualize better what is behind each cluster center. And I will be showing it tomorrow if there's time, and you will be able to play around with it. For now, it's a nice demonstration that you can now order to every point in space. It will be showing you what molecular structure is behind there. right? I think this is the first time that we see the molecule since we started. So I wanted to show this here because it is imperative that while you're doing this, well, it's imperative. It's not imperative. It's good if while you are doing all of the computations in this space of discrete indices, don't get lost because of that, okay? Behind each one of every number here, there is a group of conformations specific to that point. Actually, what we could even do at this moment, if I manage to do so, is I can show you already the difference, what it means to be on one side of the potential versus the other potential. So yes. Okay, so I'm gonna just grab a couple of samples of the molecule here. Now, you know what? It's going to be hard to see now on the fly. We'll do it tomorrow. It's not that important. So now let's play with different clustering methods. Another clustering method implemented in PyEMMA, it's pretty useless if you ask me because we never use it, but it's informative to have it there. It's just uniform time clustering. I think GROMACS also implements it because it's very easy to do. It's just you just take every nth frame of your data and you consider that a cluster center. Okay. The problem is that it's also shaped the way your data is going to be shaped. So if you visited this part of the Tika space only very briefly, you're going to end up having very little points there, and that might lead to bad discretizations, right? So this, the same thing counts here, right? This point here is having to account to whatever conformations lie in this part of space, right? So it might be that you have a discretization problem there. So you had a question.
If you go back to the line of the indices, what does this mean again? What are these indices? Are they like local minima or?
These indices is because I cannot plot a number for every point here. Okay, so every one of these blue dots, we can give it a name or a color, blue, red, magenta, or whatever. I just need to distinguish them. Okay,
yeah, okay.
So I'm going to distinguish them using numbers because they're very practical. Because
they are not sorted.
no, wait, because this is the trajectory. This is the trajectory. This is the lines, the blue lines that were standing around the value of 0 for very long, and then jumping and then going back. Now I have assigned every frame of that trajectory to one of these cluster centers, and now I can write my trajectory in this way. So this is what I was telling you, that this is like the key point where you forget that you are in the space of molecules, and now you're in the space of labels. So I'm not going to tell you anymore the tick number 1 is around 0. I'm just going to tell you the system was in state 26. Okay? And because these are, obviously, I start with this, you can name it what you want, because you could name it what you want, okay? You just need to be able to assign a frame of the trajectory to a cluster center. But if you give them indices, you can do very easily algebra on them, okay? Because you can use it to sort columns and rows of a matrix, which is in the end what we're doing here. But the numbers per se, they don't have any meaning, okay? They're just there to tell me that it's a little bit different to be in state 67 than it is to be in state 26, yeah.
I assume that you have the same number of indices as the same number of frames, right? So you have the same number of frames as the same number of indices.
The length of this trajectory
is the same.
Is the same. The trajectory, the discrete trajectory hasn't changed length. But I have. No, this is important. No. Let's do it like this, okay? I think this is pretty illustrative. This number here is the number of centers to which I am going to discretize my trajectory. I'm just going to use 2. Where am I?
I think you deleted it.
What did I do? Did I delete the...
Yeah.
You deleted something in
You
this,
deleted the sentence in this one.
Oh, sorry. Okay.
Yeah.
So where do you think k-means will put two centers?
on the two dark.
Right? So I only have two centers. I still have 20,000 frames.
Yeah. Yeah, then you only have 0 and 1.
I'm gonna just have a 20,000 frames long array of zeros and ones. 0, 0, 0, 0, 1. But okay?
Yes.
Are we arriving at the aha moment? Let's see what happens if I just give 3. Voila. You know, k-means is very good. Can you guys see the blue dot there? Okay. So now I have projected the entire complexity of my 56 atoms system to 3 little numbers. To a 3, and now I can take this string of integers and compress that into a 3 times 3 matrix, and that's your system. So the output of this supercomputer $1 million hardware, you're doing, in a sense, you're compressing it to a 3 times 3 matrix, which is awesome. You have to like that, or you could like that, but never forget that behind that discretizations and these zeros and ones, there's still the molecules there. Okay, so now this should be much easier. Yeah. So this is one conformation, the other conformation. It's a pity that they're coming out gray, because then you don't see the difference, but you can do overlays of them. I'll show it on tomorrow. Yeah. Okay?
Can I ask a question before you move on?
Yeah, let me just see how am I doing with time, because I'm like in the first third, and Tim?
We're like 30 minutes now.
Okay. Just give me a second.
I can ask later.
Yeah, if you could, that would be better. Let me just do this here. Now, before we move on, the clever among you, which didn't raise your hand before you're saying, but if you know at the beginning that you just need 3 to describe the 3 potential wells, why did you choose 100? Or that's what you should be asking, right? Like if you know that you can, there's like 3 wells, you need 3 centers, and you get this 3 times 3 matrix. Well, now we know that we just need 2 of them, right? I've just taken this complexity, projected it to a 2D plane where I can see with my eyes that there are 3 wells and that the transitions should be among these 3 wells, but that's not the case. Usually we're working in high dimensional spaces where even creating the histogram has its problems. So what you do is you put enough centers there so that one of the conditions explained by Frank this morning about local equilibrium is satisfied. I think there will be another lecture on that, but this is why what you do is you overshoot the number of cluster centers, so then you can coarse grain after the fact. Okay? Again, different types of clustering. We had the time uniform. Now we have, this is a very clear one. This is the space uniform. Okay, so I don't care about the density of the data. I just want, I need to. Okay, so now my blue points don't really represent the shape of my data. Okay, they don't care that there's much more density here than here, right? One could say that this is not that very well, not that very good a clustering method, because you are devoting the same amount of attention to the places where you have a lot of data, where the places that you have less data. Okay. Anyway, most of the time you're going to be using k-means. Now we're going to be comparing 2 types of dimensionality reductions: principal component analysis, which I'm hoping you know, and the time-independent component. And you see that the trajectories, and the free energy surface look slightly different. Now, topologically, this surface and the surface that I showed you before could, in principle, be the same. We have two highly populated minima and another one that's less populated. It could be or it could not be. I'd have to go there and see if these are the processes that are captured by the tick projection. Let's assume that they are the same. If we assume that they are the same, it means that in this particular case, PCA is a comparatively good dimensionality reduction method, because you haven't lost the information. There's two highly populated wells with a less populated, and if I were to look at the molecule, at the structures behind these wells, I'd find the same information. However, this projection is much more sensitive to clustering errors, because now your data is very close to one another, right? Imagine if I did the thing that I did at the beginning with just two cluster centers, right? Probably K-means would just put one cluster center here to account for the both of them, and you would lose the kinetic information of the system transitioning between these two. In other words, you would not be discretizing to cells that are in local equilibrium. You don't need to fully understand that. You just need to store PCA dimensionality reduction might lead to projections that are prone to poor discretizations. So the more of these problems you can clear already at the phase of dimensionality reduction, that is through doing something like TICA, the better. Because it's really hard to make a discretization error when your free energy surface looks like this, right? So regular spacing would work here. K-means works almost always. Even time uniform would also work here, because there were some frames that visited. So this is why we always featureize and then project to ticks, because they are clearing problems that could appear down the line after discretizing. Now, these details, I think I'm just going to go quickly over them, which is the different ways in which you can handle data when using PyEMMA. There's a way in which you can load everything up to memory and then perform the TICA computation and the projection from memory with variables that are all in memory. That is usually the desirable situation, because computing processes will run faster if they don't have to go back to the hard disk to read the data. The problem is very often it's the case that the full data set does not fit into memory. So what we have constructed for those cases are pipelines, where you define the stages of your analysis through the objects that are native to PyEMMA. So you say that your stage one is going to be go to this trajectory file, create a source object that immediately featureizes to these features, which were the Cartesian coordinates. Could be some other features, whatever. Stage 2 will be do TICA. But look, TICA here doesn't even have an input. We're just saying do TICA at this with this dimension, but we're not telling it with which data set. It's like an envelope. It's waiting to get the input so that it can run. And the same thing with K-means. K-means doesn't even have an input. It just has the parameter that you want 100 cluster centers. And now we concatenate stage 1, go to the file, featureize. Stage 2, project to ticks. Get ticks and project to ticks. And stage 3, cluster into one single pipeline. And it works. And you will obtain the same result as above without ever having loaded the entire dataset onto memory. It's very usual that you can have datasets in 20, 30 gigs of data. Well, it's not very usual, but it's not unusual. So we're doing it. Now, striding is just a parameter that helps speed up some of the computations. So I can use, for extracting my cluster centers, the entire dataset, or I can just use a thinned down version of the dataset that will be somehow representative. I'm not saying that I'm discarding frames of the data set. I'm just going to, at the moment of obtaining the cluster centers, I'm just going to take a reduced version of that data set. That's kind of at the moment of the parametrization. Okay, all of these methods, Tika obtention, clustering, I don't know which other methods have parametrization, like can be not parameterized, clustering, TIC, PCA, essentially anything that needs to go to the data, evaluate something, and then give an output. You can parameterize it with less data because it's going to be faster, as we can see here. So this takes, if I take all data, it takes me 1 minute, and if I just take the 10th frames, it's going to take me 7 seconds. Okay. Another important feature why we also push for the usage of Tika is that because it's not dependent on variance, which is I saw it, Steve. Because it's not dependent on variance, but it's dependent on the speed or slowness of the coordinate. It doesn't really matter if you're capturing a process via Cartesian coordinates or distance or angles, because the speed is inherent to the process, not to the coordinate. So what might look like a big change if you measure it as distance between two pairs of residues in a single molecule might look like a little change if you just watch it through the angle. But what is guaranteed is that the underlying process has always the same speed, the same kinetics, regardless of how I choose to discretize it. To represent it. Is that idea kind of clear? Right? Good. Because that means that because Tika is going to exploit that property, I can make myself independent of the original features of choice. So I can take the same system and go to the distance representation. Okay, see alpha distances here. And look, I get essentially the same trajectories as I would do with TICs and a very similar free energy surface. Hopefully. Now I'm going to move on to the MSM. Okay, so it's more or less the same representation. Sorry, the same free energy surface. It's not exactly the same free energy surface because I am using a very, very small version of the data because I'm using only 20,000 frames. And that, as with any method that depends on numerically extracting quantities, the more data you have, the less difference is going to go in the different realizations of it. So, Markov state estimation, you haven't done that in the morning, am I right? Great. So I'm just going to go through the basic steps with this data set, and then you'll do it yourselves in the notebooks that Fabian will explain, and Tim, and me, and everybody. So we import the MSM method of PyEMMA, and we estimate the implied timescales, which are these quantities over here. Now let me spend some time talking about this plot. Actually,
you can also reduce the number of times to see the coding area.
This is a nice thing of having the developers in the room. They know all of the tricks. Okay, so where is the stick of power? There it is. So these are lag times expressed in frames, and these numbers here correspond to these numbers here. And the somehow step that you have to do to fully understand this graph is a different Markov state problem has been, or a different Markov model has been estimated for every one of these numbers. So we estimated a Markov model at 100, okay, here, the solution of which are these 5 points. So although the lines are connected horizontally, because they're effectively representing the same process, they are coming from estimations of Markov state models at different timescales. Why am I, this is something that to me it's kind of important that you know that the computation of the MSM here doesn't know anything about the computation of the MSM here, okay? The only thing that they share is this string of discrete indices that represent my 20,000 frames, okay? That doesn't change because the discretization is lag time independent. So I'm always starting from there. And then I'm just like shifting my trajectory by 1 frame, 2 frames, 5, 10, 200 frames, and computing this count matrix, okay? This for blob that Frank showed in the morning for different timescales, the very same way that he showed today in the morning. And from that count matrix, I'm obtaining a transition matrix, which I am diagonalizing, the eigenvalues of which are these lambdas here. I'm taking the logarithm under minus the lag time itself to arrive at the time scale. So that these actually are frames or steps, and these are frames or steps. So there's like one MSM. You could do this plot just by writing a Python loop for tau in this vector, estimate MSM, and then you paste that all together, and then you would do this graph. So there's here one solution, here one solution, here one solution, here one solution. Now, why do we join them through a horizontal line? Because it happens that the solution is the same no matter the lag time. Okay? At the beginning, no, because if the solution were the same, the time scale would change. Okay? At the beginning, you're having to decorrelate the very fast processes. But there arrives a lag time here, after which you are almost getting the same result no matter at the lag time at which you have estimated. Which means whatever this MSM here is capturing, this MSM here is capturing as well. You have gotten rid of all of the fast processes contaminating through noise your spectrum, and you have a converged timescales plot. I spent some time here because the short version of this is just use this method until these lines look flat. If I only have like 30 seconds and I needed you to make an MSM out of your data, I would just like, don't bother me, repeat this until you get a flat plot looking like this. And that means you can choose any one model to represent your system. Okay? But now you know what's behind. Okay, so the timescales appear converge after 25 frames. So, as I told you, well, this is just advertising that you can put error bars on the timescales. We're choosing the MSM at 100 frames. Okay, so the one around here, and we're showing you the spectrum of that MSM, and the MSM has 2 slow processes, and then a gap, and then the rest of them, they're all together. Now, I've been using the word process somehow loosely until now, but you can actually only use it here. So this is an actual process. There's an eigenvector to this spectrum that represents a motion in space of the molecule that is happening at a particular time scale, and that is the process. The ticks were a linear approximation to that process. And even the features that we usually deal with, right? Like, let's say you want to study ligand dissociation, right? You have a big molecule and there's a ligand attached to it. It's obviously very intuitive and straightforward to just pick the center of mass distance between the ligand and some contact in the protein and just use that as a coordinate, right? But you would agree with me that the physical process is not the one of that distance growing, right? The physical process might be some other residue that's flipping a side chain, making an interaction much weaker so that the ligand leaves, right? So this is sort of how far off you can be with your chosen feature, okay, your feature of choice where you say, yeah, I'm gonna like do this distance. Ligand binding, absolutely, just go with the center of mass distance, you're not gonna be wrong. But if you know that your system is ligand binding, you probably know already a lot of information about it. We're dealing, as my boss said today in the morning, with systems where we don't really know what's happening. So we want to featureize into something that captures somehow the entire thing, and then make a dimensionality reduction out of it that will take me to a free energy surface that represents whatever the processes are. And these processes are the spectrum. And we're very happy that the spectrum looks like this, because it's telling me there is one process that's happening at like, these are not nanoseconds, these are whatever, 1,000 frames, another process that's happening at around 500 frames, and then the rest of them are very fast. And now you should be able to tell me which two processes are those. Which process is associated with this timescale? What's the slowest process of the system?
Transition between the slowest one,
the slowest one, right? So our ticks were actually pretty good approximations of the processes, but these are the actual processes, okay? That's sometimes going to be the case, sometimes not going to be the case. And you really have to go to the MSM to disentangle relationships between the ticks. And because there is a gap here, we can actually say, you know what, I only need two eigenvectors or two processes to represent my system. One which is taking me from the left side of the free energy surface to the right side, or from where you're standing, you know. One process which is taking me from here to here, and what process is that's taking me from, you know, switching on between. For the chemists, I'm a chemist, you should, again, use me, and because we're doing a workshop and I only have 5 minutes, associate process with free energy barrier. It's a very intuitive. So the first process is accounting for the largest free energy barrier, which is effectively here. The second process is accounting for the second largest energy barrier. It's the barrier between these two guys, and doesn't really care about this one, right? Like you're already on this side of the first barrier, and now you're just looking at the barrier between these two, okay? I think we're almost done, because what you need to do, this is, again, the eigenvectors explaining this barrier. I'm trying to make it look like, yeah. And with these three processes, right, I show you the spectrum. I told you there was one slow process, another slow process, and then they were all falling off, no? Okay, so, again, for the clever ones. If I have two barriers, how many states do I have? Oh, it's always one more, right? Like, if I have one barrier, I have two states, each one along each side of that barrier. If I have two barriers, then it means that one of the states to one of those sides of that barrier gets split up in other two, okay? So because I have two large eigenvectors, I decompose my MSM to three states. And I use the PCCA method, which is the Perron cluster-cluster analysis method, which uses all of that kinetic information about barriers and the speed at which it takes the system to evolve from one part of the from one part of the landscape to the other part of the landscape, to define the metastable states, which are the states that are long-lived that we're interested in. And PCCA actually finds these states. So these are, again, my ticks, the first tick, the second tick, and voila, there is one state that is mostly where the well that was visited only a couple of times is, another one is centered around this well, and another one is centered around here. Now, I'm asking of you to do something a bit difficult. It was difficult for me at the same time, which is you have to look at all of this and think that you don't know how the free energy surface is shaped. Right? If I show you the free energy surface just from the start, say, oh, obviously there's like three wells. There's one very, little populated well that will be visited only very so often, and then there's two more wells. If you know that, then you don't really need anything what we're offering here. We're showing you how it looks, and then showing you how the algorithms actually find that underlying structure without much input of you, but with a lot of coding from us. So there you go. You have your metastable definitions, at which you have arrived at them. You would have arrived at them even if you didn't know how the free energy looked like, just by looking at the spectrum, or first looking at the implied timescale plot, seeing that it's converged, picking out one value at which it already looks converged, looking at the spectrum, identifying a spectral gap, asking for a PCCA decomposition to the number of large eigenvalues plus 1, 1, 2, 3, and there you go. I think if we want to stay on time, I should stop here, and then we perhaps can do this explanation on the fly later in the notebooks.
No.
You know what? I'd much rather use the last 10 minutes. Right? I still have. You know, I was reading that as if I had 14 minutes left before. I didn't know that was the time. It's okay. Ask me all the questions that you want in the last 10 days, right?
So when you plot the eigenvectors, you always remove the uninteresting equilibrium vector?
Well, I didn't spend some time here. Yes, I have removed it. So when we diagonalize the transition matrix inferred from the count matrix, the eigenvectors that come out of it not only represent the processes, which I told you a lot before, but they also represent the free energy distribution, the equilibrium free energy distribution of the system, which might or might not coincide with whatever I get from just histogramming the data. I was having this conversation with somebody before, right? If your data is in equilibrium and you do a histogram of it, then obviously what you get is the free energy surface. It's like the minus log of the Boltzmann distribution of it, right? So you are extracting an equilibrium property because your data is equilibrated. If your data is off equilibrium because you didn't run your simulation long enough or whatever, imagine that I have a crystal structure. I'm seeing your question. Imagine that you have a crystal structure which is unstable, and then you start 100 simulations out of it, and then it immediately leaves the structure at which it was crystallized, okay, and it adopts some other form. Because you started 100 simulations of that very unstable frame, that frame is going to be 100 times in your data, so that when you histogram it against whatever, that frame will have a count. It's just a count that's not representative of its equilibrium, because the system natively would never go to that frame, right? So this is like very hand-wavingly the problem with just histogramming data. MSMs, however, because they consider all of the kinetics and because they exploit underlying assumptions like the data, even though it isn't in equilibrium as observed, it should be in equilibrium, can infer how the free energy distribution, the equilibrium distribution, the Boltzmann distribution should look like. And that's a very important property. Again, it's this double play that I'm telling you. Like, if you had the equilibrium distribution to start with, you probably already know a lot about your system. Fabian here in the audience has recently published a paper, which some extension of MSM methods, where what you observe is completely off equilibrium, because it's impossible to observe equilibrium because you're observing a system that takes hours, like physical hours, to equilibrate, and you're never going to simulate 1 hour, right? If the fastest supercomputer on Earth simulated 5 years ago 1 millisecond, and that was an incredible feat, imagine how long you have to wait. But still, these methods that take kinetics into account are able to recover equilibrium properties from non-equilibrium data, and that's very important.
Can you maybe say something again about the connection between the slowest process and because if I have this molecule and it has different states, and one of the states is really unlikely, or you have to wait a long time to this molecule switch into the state, how do I from that know that this state is important? Could be just some Did you get my question?
Well, you haven't asked a question because you haven't told me what important means. So what, like, try to ask the question without the word important.
Why is the slowest process connected to the cluster in the plot? Maybe that's.
Which plot is best for your question?
Yeah, that one. Maybe this one or the yeah, that one. Yeah. That's,
The actual one,
yeah,
like
yeah, this one.
yeah.
So why are these?
Why is it
If we only
important?
had like if we,
Why is it important that we sample this if it has so little population? Like, what would be the problem of having a trajectory that never went here and it's just these two? Is that you're not getting it? I mean, perhaps this was said very early at the beginning. The slowest process of the system are the ones that interest us because they are actually governing the long-term dynamics of the system.
yeah, exactly. How do you know that?
Well,
I don't see this connection. Why? Because you have a process that's really unlikely, but how do you know that it's actually influencing the whole dynamics of your molecule? How do you know that? Because it could be just something at the end of your really long chain that just takes forever to reach this one position, but it doesn't really say anything about 95% of the molecule. Or
so
is
that's a very good question, and so there are assumptions that. So why should you care? Because until you have observed that, your system is out of equilibrium. So that's like my first. Like if I were to know the entire phase space and I were to do a Boltzmann inversion of the no, not a Boltzmann inversion. If I were to compute the energy of every possible configuration of the molecule and then just do, you know, the Boltzmann distribution based on that, then there would be like 5% of my population here. And if it isn't in my data, you're saying like, well, who cares? Like 5% of the population. This is like essentially your question. And you should care first of all because until you don't have that 5%, then your data is out of equilibrium. But there is also a false friend, which is 5% of the population. Like you have to think in logarithmic or exponential terms. Okay, so what might be, as Frank said this morning, right? Like what might be an error of 1% in population translates to I don't know how many energy errors when you do it at 25. I think it was like 2 or 3 kT, and then at room temperature I don't know how much that is, but it's again. If you know that this state is unimportant, then you're right. You're like, yeah, you know, it only goes here 5% of the time, and the molecule is only biologically active here. Yeah, but if you already know that, what are you doing simulating this molecule? You understand? Like,
we don't know if it's important.
Which brings me to my first answer, which is define important.
Yeah.
So you have to observe and then discard, which is what we usually have to do. There is a more operational answer, which is you can still produce actionable information out of off-equilibrium data. A lot of simulations with huge molecules, they say, well, while we're simulating, there is a helix somewhere that's slowly unfolding, but we're not going to take that into account because we assume that what we're interested in is not affected by the state of the helix. They are kinetically uncoupled.
Okay,
but it's an assumption that you have to buy into.
And if we do 100% of the simulation, then we might know if it affects it.
There is another thing, which is you should know everything about your system, because if you know that there is a well here, you might think about doing a mutation that destabilizes these two guys so that you actually favor the state here, and it turns out that with this drug is much more potent, whatever. So if you produce a mutated version of the drug that just reweights the potential so that this is much more stable, then you might get new properties. This is like a pretty far-fetched, but you don't know what you can do with what you don't know. You have to know first and then discard. I'm gonna go with you. No, one minute.
So you say toward the end that with after building MSM and so forth, you get some metastable states, and that basically you get that even if you didn't know the shape of the energy landscape, right?
Yeah.
But to obtain your MSM, you did the TICA analysis, which provides you with like some sort of energy landscape to the most important coordinates.
Yeah.
Would you get the same answer if you didn't do the TICA, if you just do like the MSM on the without doing the dimensional reduction?
If it's a system like a dissociation where you can discretize on the center of mass ligand to the substrate, then you could, okay, because you're pretty sure about your system. But I have spent 4 years working on a system where they know how it looks at the beginning, they know how it looks at the end, but they don't really know how it transforms from one to the other. So what you do is you featureize as much as you can, throw in the contacts, the angles, the positions, whatever, and then just let it run through TICA and see if TICA arrives at the reduced version of it, which is nevertheless going to be high dimensional, and I would be here showing you 19 2D plots to cover the first 20 ticks. But still, PCA would work, and I would ask, and the spectrum, the spectrum of a matrix is just like a string of scalars, no matter how dimensional the matrix is. So I can have like a 300 times 300 matrix, and I just have to look at the first 10 numbers and say, I'm going to like 3 states. And then I do the PCCA decomposition, which is going to give me these blue blobs that I was showing you before. Now you've seen like my password and everything. Right? So this PCA, I will be able to say, where is the darkest blue in my 20-dimensional space? But I could go, please provide me with 100 samples of the point in space that maximizes the membership function to PCCA set 1. And then I would look at 100 structures from here, 100 structures from here, 100 structures from here, regardless of in what space I am operating. And that's actually what you will be doing later, because this is exactly what you're doing here. So each color represents sample structures from the points in space where these blue clouds were the darkest. And when you overlay them, you see that the red one is different from the blue and green ones, and this is the slowest process right here. So going from either one of these two, the red and the green, the blue and the green, to the red one, that's the slowest process. So to go back to your process, I could live in a world where I don't know that this red thing exists until somebody finds out that this thing cures cancer, whatever. So you really want to have it there. So I would arrive at this picture where I can see with my eyes what's going on, even if I had clustered in a 100-dimensional space of I don't even know where I'm clustering in. So, yeah.
I'm wondering, and I think I'm a bit lost, where exactly the Markovian property is important.
In the time scale
where would it fail? I mean, what I'm imagining is that my ability to cluster the energy landscape and say transitions happen independently in this landscape. That's precisely what I call Markovian.
Yeah, so we haven't showed it here, but if your decomposition into these 3 blobs is done correct, and it should be correct if you have decomposed to the number of large eigenvalues before this gap plus 1, then I can re-discretize my system into just these 3 labels, right? It's like what we did at the beginning, where I just gave you 0, 1, and 2, and then with that, it's only now I know that it's right. I could re-discretize my system onto those labels and perform Markovianity tests on the dynamics coming out of this relabeling. And if these Markovianity tests stand, it means that these are actual metastable states, and I don't really need to know anything more about the system. Right? It's just come on, Moritz, ask your question.
I was just wondering if we're actually doing that. But I said no.
The Markovianity test of that? We're not doing it per se like this. We're checking the rate at which these states get depleted of population against the rate that our Markov model predicts. That's the so-called Chapman-Kolmogorov test. And if the rate is the same for all state definitions, if your prediction about how stable a part of space is actually coincides with how that part of space was stable in your actual data, then you say that your state definition is a good definition. So that's where you check the Markovianity, and because you want to pass that Markovianity test, you choose a model where the time scales have converged. So this is, to me, this is then the non-memory, or the memory, this is the non-memory here, right? Regardless of where you look at the system, if every 50 frames or every 100 frames, it's just always the guy before me, never.
So that means also on very small timescales, you could say the system probably doesn't behave completely Markovian.
Yes, here. But it's actually, the system at the microscopic level is Markovian, because the Newton's equation of motion are just x plus, right? So x at t plus dt is a function of x, so that's Markovian, no matter, it doesn't get more Markovian than that. But you have created a discretization where it introduces fake memory effects. Okay, I think I'm done with time.